What we really wanted to achieve here is like, well, why make this really fast car that an electric car is the best car?
In an industry already charged with innovation, Elon Musk has just dropped another bombshell with Tesla's new condensed super battery that comes with only a 15-minute charging time. With promises of faster charging, ultra-high energy density, and driving ranges approaching 1,000 kilometers, this battery doesn't just raise the bar, it hurls it into a different stratosphere. What makes this moment even more compelling is the timing. As Chinese giants like CATL and BYD dominate the EV battery space with scale and affordability, Musk steps forward not just to compete, but to transform. Let's dive straight in.
Upstate facility is showing us its new technology to advance the future of electric vehicles.
Tesla's battery evolution. When Tesla was founded in 2003 by engineers Martin Eberhard and Mark Tarpenning, and later transformed under the leadership of Elon Musk, it faced a hostile automotive landscape. At the time, electric vehicles were largely dismissed as impractical novelties, limited by sluggish performance, short range, and prohibitively expensive batteries. The global auto industry was entrenched in the internal combustion engine, and even early hybrids like the Toyota Prius were viewed with skepticism in some markets. But Tesla saw something else. The key to making EVs mainstream wasn't just in sleek car design, but in breaking through the limitations of battery technology. From the outset, Tesla focused heavily on batteries, treating them not as off-the-shelf components, but as the very heart of its vehicles. The company's first production car, the Roadster, was built on the chassis of a Lotus Elise, but packed with over 6,800 lithium-ion 18650 cylindrical cells, the same type commonly used in laptops. Manufactured by Panasonic, these 18650 cells were repurposed and repackaged by Tesla engineers into a novel battery pack configuration. This move was radical. No major automaker had used consumer-grade lithium-ion cells on such a scale in a road vehicle. Yet this allowed Tesla to bypass traditional battery suppliers and deliver the Roadster with a then unheard of range of over 200 miles, around 320 kilometers per charge, something no EV had achieved at the time. But Tesla wanted more. The EV manufacturer deepened its collaboration with Panasonic and laid plans for something unprecedented in the auto industry: a vertically integrated battery manufacturing facility. In 2014, Tesla announced the Gigafactory near Sparks, Nevada. By the time its first phase opened in 2016, the facility was the world's largest building by footprint. The idea was not only to produce battery packs in-house, but also to streamline the supply chain, cut down manufacturing costs per kilowatt-hour, and scale EV production to meet global demand. This move paid off. Tesla's second major cell innovation came with the Model 3, launched in 2017. Here, Tesla shifted from the older 18650 cells to the more advanced 2170 format, a cylindrical cell measuring 21 mm in diameter and 70 mm in length, developed jointly with Panasonic at the Gigafactory. These 2170 cells were a technical leap forward, offering higher energy density, better thermal management, and improved longevity compared to the 18650 batteries. They enabled Tesla to offer longer-range vehicles at more competitive prices, cementing the Model 3 as the best-selling EV globally in subsequent years. But the biggest leap in Tesla's battery roadmap came during its much-anticipated Battery Day on September 22, 2020. It was here that Elon Musk and Tesla SVP Drew Baglino unveiled the 4680 tabless cell, a revolutionary design that marked a sharp departure from previous formats. At 46 mm in diameter and 80 mm in length, the 4680 offered 5 times the energy, 6 times the power, and a 16% increase in range compared to the 2170. More importantly, its tabless design, eliminating the internal tabs connecting the electrodes, reduced resistance and allowed for faster charge and discharge cycles while simplifying manufacturing. Tesla also introduced structural battery packs, where the 4680 cells would become part of the vehicle's chassis itself, improving rigidity and reducing overall mass. The manufacturing improvements tied to the 4680 included Tesla's new dry electrode coating process, acquired through its 2019 purchase of Maxwell Technologies. This technique eliminated the need for wet solvents in electrode production, cutting both cost and environmental impact. Since 2021, limited volumes of the 4680 cells have been produced at Tesla's pilot line in Fremont, California, and later scaled to Giga, Texas, near Austin. These cells now power select versions of the Model Y and Cybertruck, but it was clear this was a transitional phase leading towards something even more ambitious. That ambition materialized in 2025 with the reveal of Tesla's condensed battery, the culmination of 2 decades of research, thousands of patents, and multiple manufacturing revolutions. Though details were tightly held prior to launch, the condensed battery represents a shift from lithium-ion to a new solid-state adjacent chemistry incorporating silicon nanowire anodes and high-nickel cathodes. This leap has resulted in significantly higher volumetric and gravimetric energy density, estimated at over 450 watt-hours per kilogram, compared to around 250 watt-hours per kilogram for the 2170 cells. The result is a longer range, faster charging, and drastically lower thermal risk. What is Tesla's condensed battery? Tesla's condensed battery is the next leap in energy storage, designed to redefine the metrics of performance, efficiency, and safety in electric power systems. Officially revealed in 2025, the condensed battery is the culmination of over 15 years of Tesla's vertical integration in battery research, from cell architecture to raw material processing. Unlike traditional lithium-ion batteries, this system packs significantly more energy into a smaller footprint, while also offering advancements in durability, charging speed, and environmental sustainability. At the heart of this new system is its unparalleled energy density. Tesla's condensed battery exceeds 450 watt-hours per kilogram, a notable increase from the 250 to 270 watt-hours per kilogram achieved in the 2170 cells used in the Model 3 and Model Y, and the roughly 300 to 330 watt-hours per kilogram achieved by the newer 4680 cells, powering select versions of the Cybertruck and Model Y. The leap in energy density means that vehicles equipped with these batteries can achieve longer driving ranges, potentially over 800 kilometers or 500 miles per charge, without increasing the physical size or weight of the battery pack. This makes the battery ideal not just for automotive applications, but also for drones, aircraft, and portable power systems where space and weight are critical. One of the most transformative elements in the condensed battery is the use of silicon nanowire anodes instead of traditional graphite. Silicon has long been considered a superior anode material due to its ability to store up to 10 times more lithium ions per gram than graphite. However, the major drawback had always been expansion. Silicon swells up to 300% during charge cycles, causing degradation and reducing battery lifespan. Tesla, building on research from acquired companies like Maxwell Technologies and collaborating with research teams in Texas and California, developed a nanostructured silicon architecture that mitigates this swelling. These ultra-thin nanowires allow lithium ions to flow more efficiently while maintaining structural integrity, leading to both higher capacity and better cycle life. Complementing the silicon anode is a solid-state electrolyte, replacing the liquid electrolyte used in conventional lithium-ion cells. Solid-state electrolytes, typically made from ceramics, sulfides, or polymers, offer significant safety improvements. They are non-flammable and eliminate the risk of leakage, overheating, or explosion caused by dendrite formation or thermal runaway. Tesla's electrolyte blend is believed to be derived from lithium phosphorus oxynitride, or LiPoN, with proprietary stabilizers, enabling high ionic conductivity and stability across wide temperature ranges. The result is a battery that can withstand extreme thermal and mechanical stress, opening doors for aerospace and military applications. On the cathode side, Tesla has opted for a high-nickel, low-cobalt composition, a shift that began with the 2170 and 4680 cells, but is now refined to new levels. Traditional NCA or nickel-cobalt-aluminum cathodes typically contain 80% nickel, but the condensed battery's formulation pushes this to 88 to 90%, drastically reducing cobalt content, which is expensive, ethically controversial, and environmentally damaging to extract. This change not only improves energy density, but also aligns with Tesla's broader supply chain goals, reducing reliance on cobalt mining in the Democratic Republic of the Congo and increasing use of North American and Australian nickel sources. What truly sets the condensed battery apart is its cross-sectoral versatility. While Tesla's EVs are the primary deployment target, the company has designed this battery to be modular and scalable. In 2024, Tesla's energy division began testing condensed battery modules in its Megapack systems at the Moss Landing Energy Storage Facility in California. The results showed a 38% increase in power output and a 25% decrease in thermal management costs compared to traditional LFP-based packs. Elon Musk has also hinted at applications in Tesla's Optimus humanoid robots and SpaceX's Starship systems, where high-density energy is essential and space is at a premium. Another key factor in Tesla's condensed battery is the manufacturing ecosystem surrounding it. Tesla's battery materials refinery in Corpus Christi, Texas, which became operational in early 2024, supplies key inputs like battery-grade lithium and nickel. This facility supports Tesla's strategy of vertical integration, reducing dependence on external suppliers and minimizing geopolitical risks. In tandem, Giga Nevada and Giga Texas are scaling up pilot lines dedicated to condensed battery production using Tesla's dry electrode coating and advanced thermal compression bonding, which reduces water usage and simplifies cell assembly. The unveiling of the condensed battery in 2025 marks a new era in energy systems, but Tesla has made clear that this is not the final form of EV innovation. With enhanced performance, recharge times under 15 minutes for a full charge, and dramatically lower fire risk, the condensed battery has the potential to accelerate the mass adoption of electric vehicles, autonomous systems, and distributed energy grids. Technological turning point. The unveiling of Tesla's condensed battery in 2025 marks a definitive technological turning point, not only in the electric vehicle sector, but across the entire energy storage landscape. Unlike prior advancements that chipped away incrementally at battery limitations, this innovation delivers substantial, measurable improvements in energy density, safety, charge time, and longevity. These gains are not theoretical or aspirational. They are now being implemented into early-phase production systems and are expected to scale through Tesla's gigafactories, starting with Giga Nevada and Giga Texas by late 2025. The implications are vast and quantifiable. Cars capable of driving 1,000 kilometers or 620 miles on a single charge, smartphones that operate for up to 5 days, and stationary batteries that can power entire off-grid communities or neighborhoods using renewables alone. The condensed battery achieves these milestones through a combination of technical refinements: silicon nanowire anodes that store nearly 10 times more lithium per gram than graphite, solid-state electrolytes that replace flammable liquids, and high-nickel, low-cobalt cathodes that reduce reliance on expensive, geopolitically sensitive, rare earth elements. The result is a battery with up to 450 watt-hours per kilogram energy density, a major increase from the 270 watt-hours per kilogram provided by Tesla's 2170 cells, or the 290 to 300 watt-hours per kilogram range for the 4680 format. By integrating these condensed cells into a new platform architecture, tested on a Model S prototype and an experimental Powerwall X, Tesla effectively eliminates range anxiety, a long-standing barrier to widespread EV adoption. Consider the direct consumer implications. A mid-sized sedan equipped with a 100 kilowatt-hours condensed battery pack can achieve over 1,000 kilometers of real-world range, verified during controlled track tests at the Fremont facility in April 2025. This is more than double the range of the average EV on roads today. Furthermore, this range does not come with a weight penalty. In fact, the condensed pack is 17% lighter and 23% smaller than its 4680 counterpart, enabling more flexible vehicle layouts and improved handling dynamics. For public transport, trucking, and electric aviation, such compact energy density opens the door to unprecedented use cases, including fully electric short-haul aircraft and heavy-duty trucks capable of cross-country freight routes without a single recharge stop. Moreover, the technology significantly reduces cost per kilowatt-hour. By transitioning away from cobalt-heavy chemistries, since cobalt has hovered around $3,000 per metric ton, and instead emphasizing high-nickel, silicon, and aluminum components, Tesla has slashed raw material costs by over 20%. Coupled with their vertical integration strategy and ongoing automation at gigafactories, the company expects a battery price of $55 to $60 per kilowatt-hour at scale by 2026. This is a crucial threshold. At $60 per kilowatt-hour, EVs become cost competitive with internal combustion engine vehicles even without subsidies, making clean transport more accessible across income brackets and global markets, including countries in South Asia, Africa, and Latin America. The condensed battery also provides a viable foundation for electric aircraft, which had previously been constrained by the limited energy density of lithium-ion systems. In collaboration with SpaceX and a California-based aerospace partner, Tesla's energy division has initiated trials for lightweight modular battery packs for unmanned aerial vehicles and short-range passenger flights. These packs, tested at Edwards Air Force Base in early 2025, sustain up to 2 hours of continuous flight time on a single charge, double the previous record for electric-powered fixed-wing craft. But all is not well for Tesla. Biggest challenges Tesla faces. Tesla's introduction of the condensed battery signals a seismic shift in energy storage. Yet the path to full deployment is paved with formidable challenges, rooted in engineering, geopolitics, economics, and public trust. The technology's advantages are real, but their realization at a global scale requires overcoming very specific and measurable hurdles. One of the most immediate obstacles lies in manufacturing complexity. The core innovations behind the condensed battery, silicon nanowire anodes, and solid-state electrolytes are not simply drop-in replacements for existing lithium-ion technology. Silicon nanowires, for example, must be grown in controlled environments using chemical vapor deposition systems that require submicron-level precision, similar to those used in semiconductor fabrication. This process is expensive, sensitive to contamination, and not easily scalable without cleanroom-grade environments. Solid-state electrolytes, meanwhile, must be deposited uniformly and without microfractures to ensure both conductivity and safety. Building production lines to handle these materials at the gigafactory scale, Tesla's benchmark since the Nevada facility opened in 2016, demands not only new equipment but also retrained labor, upgraded automation systems, and significant time. Even a minor imperfection in electrode layering or electrolyte application can lead to total cell failure. Scaling this from prototype batches to millions of cells per month at Giga Texas or Giga Berlin involves not just technical retooling, but full system reintegration. Closely tied to production challenges is the issue of material availability. While Tesla has deliberately moved away from cobalt, long criticized for both cost and its link to unethical mining in the Democratic Republic of Congo, the demand for high-purity lithium, refined silicon, and nickel-rich cathodes has surged. Tesla sources lithium from the Silver Peak mine in Nevada and through deals with Australian firms like Piedmont Lithium. but global lithium prices have remained volatile, reaching $70,000 per metric ton at peak in late 2022, before stabilizing to around $20,000 per metric ton in 2024. Even at reduced cobalt levels, cathode production requires nickel of specific purity, which is not abundant and is geopolitically sensitive. The Philippines, Indonesia, and Russia are major players in nickel exports, and geopolitical instability or export restrictions could disrupt supply. Moreover, battery-grade silicon used in Tesla's nanowire anodes must be produced at 99.9999% purity, a process controlled by relatively few firms in the US, China, Japan, and Germany. In short, Tesla's material strategy must now evolve from price negotiation to geopolitical risk management, requiring vertical integration or long-term contracts with strategic reserves and mining operators. On the economic front, Tesla faces high initial costs associated with R&D, prototyping, and industrial scaling. The condensed battery is not a marginal evolution. It required billions in investment across multiple departments, including the Tesla Advanced Battery Research Facility in Canada, co-run with Jeff Dahn's Dalhousie University Lab. Prototypes produced between 2023 and 2024 were estimated to cost over $130 per kilowatt-hour, double the industry target for cost-effective electric mobility. To hit mass-market viability, Tesla must reduce that to $60 per kilowatt-hour or lower, requiring exponential improvements in automation, yield rates, and manufacturing throughput. Elon Musk has hinted at 3D-printed electrode substrates, AI-managed factory lines, and modular manufacturing cells as part of the company's next-gen scaling strategy, but these are still in experimental phases. Every minute of factory downtime or rework caused by unstable process control at scale adds millions in losses. Regulatory hurdles compound the difficulty. Condensed batteries use materials and chemistry combinations that fall outside existing certification categories. Whether it's the US National Highway Traffic Safety Administration, or NHTSA, the Federal Aviation Administration, or FAA, or the European Union's REACH standards, Tesla must secure approvals on dozens of parameters, ranging from thermal runaway behavior to post-crash electrical stability. For example, the FAA is notoriously cautious about adopting new battery technologies in civil aviation following the Boeing 787 incidents with lithium-ion packs in 2013. Solid-state packs must demonstrate not just lab-tested safety, but consistent, real-world performance across wide temperature ranges, altitudes, and load conditions. Approval cycles can take 18 to 36 months per region, which could delay commercial applications in sectors like air mobility, grid storage, or even public transport. Lastly, Tesla must address consumer adoption barriers, which, though less technical, are equally vital. While Tesla enjoys brand loyalty among tech enthusiasts, mass-market EV adoption still lags. In 2024, EVs accounted for only 8.6% of global vehicle sales, with range anxiety, charging time, and cost cited as major deterrents. Introducing a radically new battery architecture, one that operates differently, charges faster, and lasts longer, could be perceived as risky by mainstream buyers. Public understanding of terms like solid state or nanowire is minimal. Consumer confidence will hinge on transparent data, third-party validation, and performance consistency across weather, geography, and use cases. Tesla's past experience with fires, software bugs, or controversial autonomous driving features makes trust building all the more critical. The condensed battery may well redefine what's possible, but only if these real structural challenges are met with the same ambition that produced the breakthrough itself. But Tesla's problems don't end here. Tesla's biggest challenge: Elon Musk. In early 2025, a movement known as Tesla Takedown emerged targeting Elon Musk's growing political influence and Tesla. As a grassroots, non-violent campaign, it began in February 2025 and has since spread across the US, Canada, Europe, Australia, and New Zealand. The movement spans well over 250 cities, with coordinated demonstrations urging consumers to sell their Teslas, boycott purchases, and divest from Tesla stock to hit Musk's financial standing, both symbolic and practical. Fueled by Musk's high-profile role as head of the Trump administration's Department of Government Efficiency, or DOGE, a civic restructuring office behind mass federal job cuts, the campaign views Tesla's brand as a proxy for Musk's political actions. Notable provocateurs like actor Alex Winter, sociologist Joan Donovan, and activist Valerie Costa have lent their voices, with some protests taking on a cultural tone, such as Dance Against Doge flash mobs outside dealerships in Washington, D.C. However, the movement hasn't been limited to peaceful picket lines. In Europe, including cities like Toulouse, Ottersberg, Rome, and others, multiple Tesla dealerships and supercharger stations have been burned or vandalized, sometimes coinciding with takedown events. Although the protesters maintain that they neither condone nor orchestrate such acts, law enforcement in France and Germany describes several of these incidents as potentially extremist. Tesla posted a 13% drop in global vehicle deliveries in the first quarter of 2025, delivering 361 units, compared to 388,000 in the first quarter of 2024, which was already the lowest quarterly figure since 2022. European registrations fell sharply: 61% loss in the Netherlands, 64% loss in Sweden, and 37% loss in France, with Tesla's European market share contracting from 1.3% to just 0.7% by May 2025. In parallel, the stock has dropped nearly 30 to 35% year-to-date, erasing more than $150 billion in market valuation and pushing Tesla below the $1 trillion market cap threshold for the first time since late 2024. Tensions spiked even further in May 2025 when Musk criticized Trump's One Big Beautiful Bill, a sweeping budget proposal that, among other things, would strip EV tax credits of up to $7,500 per vehicle and dismiss Tesla from eligibility for federal contracts. Trump retaliated, threatening to cancel Musk's existing federal contracts, including partnerships related to Starlink and SpaceX, and even revoking EV purchase incentives. The market reacted swiftly. Tesla shares plunged 14% in a single day, eliminating roughly $150 to $152 billion from its valuation and shaving about $27 billion off Musk's personal net worth. While global EV adoption rose 15%, Tesla's shipments fell, particularly in politically liberal markets linked to anti-Musk sentiment. States and countries aligned with progressive voters registered sharp drops in repeat Tesla purchase intent. A JP Morgan analysis forecasts a $1.2 billion annual hit to Tesla's profits from lost EV subsidies, with an additional $2 billion at risk if Senate moves limit California's zero-emission vehicle mandates. Analysis from Wedbush Securities described the 2025 first quarter performance as a disaster on every metric, attributing lost deliveries, possibly 80,000 units, to brand impact rather than factory capacity. Ross Gerber, an early Tesla investor, has publicly cautioned Musk to choose between Tesla and politics. Trump has also indicated readiness to label dealership vandalism or arson as domestic terrorism, which could justify federal prosecutions and intimidate protest activity. Meanwhile, law enforcement, including the FBI, DOJ, and ATF, are mobilizing on both violent incidents and peaceful demonstrations at Tesla facilities. However, at this point, Musk is out of allies. When Musk sharply criticized Trump's One Big Beautiful Bill on X, labeling it a disgusting abomination, it marked a breaking point between the two unlikely allies. Though Musk later issued a regret post about his harsh criticism, his relationship with Trump remains tense. It all started with Trump's trade war with literally the whole world. Musk was never on board with this. He warned the US government directly that new tariffs on Chinese imports, ranging up to 145%, would undermine American companies. Tesla's 40% dependency on Chinese-sourced battery components meant that such policies would raise production and sales costs sharply. Tesla was forced to halt orders on its Model S and Model X imports in China in April 2025 due to retaliatory 125% tariffs there. Although Model 3 and Model Y continued production in Shanghai, these two models accounted for just around 2,000 units in China, compared to over 661,000 Model 3 and Y units produced and sold locally, highlighting the disproportionate impact on US-built EV models. Tesla's standing in China, long its largest international market, deteriorated sharply. The Shanghai plant output for the first quarter of 2025 was down 22% year-on-year, contributing to a full-quarter global delivery decline, the lowest since 2022. Tesla is now the third largest EV brand in China, behind domestic leaders like BYD and NIO, with consumer sentiment increasingly sour due to Musk's political associations and imported tariffs. As if this was not enough, in March 2025, Tesla issued its largest recall yet, 46,000 Cybertrucks, to fix unstable trim and unsecured accelerator pedals, posing a braking hazard. Combined with delays transitioning Cybertruck production from pilot lines in Giga, Texas to full capacity, these build quality and rollout problems have further eroded consumer trust. These overlapping setbacks have left Musk with nowhere to turn. Without allies in Washington, Beijing, or among global consumers, Tesla's position is perilously exposed. US EV incentives may evaporate, and federal contracts may be revoked. In China, Tesla risks permanent sidelining if orders and assembly remain curtailed. Quality issues like the Cybertruck recall only extend the erosion of its brand identity. Unless Musk can reconcile his political entanglements, reassure international and domestic consumers, and restore operational excellence, Tesla risks losing its footing to rivals like BYD, VW, and others pivoting into the EV space. Tesla may implode, but even if it doesn't, the road ahead is brutal. Tesla versus BYD and other Chinese competitors. In the first quarter of 2025, a landmark shift took place. Chinese EV giant BYD, based in Shenzhen and co-founded by Wang Chuanfu in 1995, delivered 416,388 electric vehicles, a 38.7% increase year-on-year, while Tesla saw a 13% drop, delivering 336,681 EVs, its lowest quarterly total since 2022. Tesla no longer holds the mantle of the top EV seller globally. BYD has surpassed it in total volume, propelled by both pure EVs and plug-in hybrids. Europe has been especially volatile. BYD outsold Tesla in April 2025 with 7,031 EVs to Tesla's 7,065, marking the first time it has done so. BYD's Blade battery, launched in early 2020 in the Han sedan, is central to this surge. It uses lithium iron phosphate, or LFP chemistry, offering 160 watt-hours per kilogram gravimetric density, around 355 watt-hours per litre volumetric, lower than Tesla's high-nickel 4680 cells, but excels in safety, heat dissipation, and cost efficiency. The Blade's prismatic design allows for over 50% better space utilization and resists thermal runaway even under penetration tests. Its robust safety profile helps offset the lower density, making BYD's EVs cheaper and more reliable in mass production markets. Tesla's advantages lie in cutting-edge battery chemistry, autonomy software, and manufacturing innovation. The 4680 cell, introduced at Battery Day 2020, delivered 241 watt-hours per kilogram and 643 watt-hours per litre, but generated 2.3 times more heat under a 1C load compared to BYD's blade cells, necessitating advanced cooling systems. Tesla's chemistry also depends on high nickel, low cobalt cathodes and tabless cylindrical design, a clear technological edge, yet offset by engineering demands and cost. However, that edge is under threat. BYD has bolstered its global presence significantly. Sales of Chinese EVs in the UK, for example, rose to 9.4% of total car sales in May 2025, up from 5.5% a year earlier, driven primarily by BYD's models like the Dolphin Surf, priced at £18,650 or $23,000, substantially lower than the Tesla Model 3's £30,000 to £35,000 range. This aggressive pricing, fueled by BYD's vertical integration from battery production to EV manufacturing, demonstrates a clear cost advantage. BYD produced over 4.27 million vehicles globally in 2024, with 70% of components in-house, resulting in higher margins and economies of scale. China's CATL is another formidable competitor, with 2021 global market share at 32.6% and a production capacity of 96.7 gigawatt-hours, targeting 500 gigawatt-hours by 2025 and 800 gigawatt-hours by 2030. CATL is spearheading innovations like sodium-ion batteries and hybrid chemistries. BYD itself plans to launch 1,000 kilowatts ultra-fast charging systems, which will add 400 kilometers of range in 5 minutes. In contrast, Tesla's strength lies in its intense R&D and tight vertical integration, with gigafactories and refining operations like Corpus Christi, enabling direct control over key supply chains. However, political turbulence has weakened Tesla's standing with policymakers at a time when Chinese-backed rivals like BYD and CATL are surging ahead globally with affordable, scalable, and well-subsidized EV models. Tesla must balance innovation with political stability and regulatory alignment. Otherwise, it will lose the EV race. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.